everybody. Thanks again for the invitation. It's really great to be back. Today I'll talk about observations, optical observations, core collapse supernova. Since it's a very big field, I will focus mostly on stripped envelope supernova, and we'll show some of the work that we've been doing at NYU, including postdocs Federica Bianco, who's actually the co-chair of the LSST transient team, or Grau, who just received the NSF postdoc, who'll be here at CFA starting this fall, Shan Huang, who's a postdoc, Hiran Fin, and Yuxin Liu, who are both graduate students at NYU. So I would like to just remind ourselves of the supernova classification scheme, since I'm the first optical talk in that sense. So supernova are classified based on hydrogen. If it's present in the spectra at around maximum light, it's called a type 2, and if it's not present, it's a type 1. Of course, the most famous type 1s are the 1As that are shown up here. And then we have 1Bs that don't show hydrogen, but show helium, and then 1Cs that don't show helium and hydrogen. And the last 20 years, we've had broadline type 1Cs, so similar to 1Cs, but with broad absorption lines, much broader than in a normal 1C by a factor of 3 or so, that are the only types that are connected with long duration gamma bursts. So these broad lines, they get high expansion velocities, and when people use the spectra and light curves to model them, they obtain large kinetic energies, 10 to the 52 ergs, that also Adam alluded to, and that's why we call them hypernova. However, because this number is very model dependent, we've been stopping calling them hypernova and just call them by the phenomenological aspects, the broad lines, that are always the case in all supernova connected with gamma bursts. Of course, we have some kind of transition objects to 2Bs that show strong hydrogen lines, but then those hydrogen lines disappear over time, and we see strong helium lines. And of course, in the last couple of years, the last 10 years, a number of exotic transits have been observed, discovered, and paid attention to that we'll hear about later, the superluminous supernova, the type 2s and the 1Cs, the rapid transients that Maria and others will talk about, and the type 1Bns. And that's, of course, in part due to the other kinds of surveys that we have, these untargeted surveys, but also because we're paying attention to them. No longer just pay attention to the 1As for cosmology, but also various other kinds of subtypes. Now, in terms of the progenitor systems that we'll hear afterwards by Selma, we think and have seen type 2s from red or blue supergiants explode, and 1Bs come from massive stars that have no longer the hydrogen layer intact, but we see the helium layer, so that's why we see the helium lines in the spectra, and 1Cs are from the most stripped stars that no longer have hydrogen and helium intact before the explosion. And the long duration gamma bursts make only a subset, just 1% of all 1Bs and 1Cs. The question still remains, what distinguishes progenitors of supernova GRBs from those of other kinds of supernova without broad lines? And specifically, when we show this kind of cartoon, we say that there's no helium, but there's been some discussion whether there's some hidden helium, which I will address later. So in terms of the field of observational work in this area, in the last 5 years, we've seen a transition to really big data. And I'd like to make note of that. In particular, for type 2s, we've had large data sets released and thoroughly analyzed. And so there are a number of people just in the last couple of years that have had interesting papers that still debate whether there's a distinction between 2Ps and 2Ls and what it tells us about the progenitor. And then also in the 1Bs, 1Cs, we've had lots of data sets released, including ours that I'll discuss, and then also analyzed with thorough methodological studies. Not only are these data published, but also compiled. So I'd like to specifically give a shout out to the Open Supernova Catalog that was just released recently, which I think is very laudable because they put together, I'm sure, a lot of effort and time to collect all the spectra and light curves of historical or recent supernova that have been published and put them in this data set. And that's led by James Parent and Margutti, James Gauthier, Parent Margutti. So looking at this new area of statistical studies, we can see them as really treasure trove, where we can find a lot of interesting trends that answer a number of outstanding questions that we have in the field that I'll discuss. So recently, 2 years ago, we released a large CFA data set of stripped envelope supernova that include both photometry and spectroscopy. And so putting together 15 years of CFA data, we have published 73 stripped supernova in the spectroscopy and 64 stripped supernova in photometry, including near-infrared bands that doubled the world supply of well-observed stripped core collapse supernovae. So just to remind ourselves, what's important is that we have lots of spectra as a function of time. So as mentioned, some of the classification might be time dependent, and so the more spectra we have over many phases, the better it is to understand the ID and therefore the makeup of the progenitor before explosion. We have also lots of early time spectra, and we have around 10 spectra per supernova. And in some cases, actually in many cases, we had to re-ID 1/3 of the sample. So we had to re-ID 1/3 of the sample, mostly the stripped envelope of 1Bs and 1Cs. And so to be aware when one does these kinds of studies is that the supernova catalogs that still reflect the initial ID might not be correct. And it turns out many of the 1Cs are actually 1Bs. And there are many reasons for that. One is that actually the SNIT template database that includes a library of spectra where we think we know the ID had the wrong ID to begin with. And so when you propagate that into your new ID, then you get, so in that data set, in that library, actually a 1B was mislabeled as a 1C. The second thing is that people still don't remove telluric absorption in their spectra. They still put an Earth sign like 200 years ago and their plots and say this is due to the atmosphere. However, that range is actually in the range of where some of these important helium lines are, so it's really important to take out the effect of atmosphere, which we hopefully can do in the 21st century for all our data. Also, we have lots of spectra. So the 1Bs have helium lines that take some time to develop because of non-thermal excitation effects due to nickel. And so it's really important to have lots of spectra also at late times around maximum later to ID your spectra correctly. So all our data are freely available on the CFA archive and also on WISE-REP, which is another large data collection website where we can download published data. And we also have released our new and modified SNIT templates that people can use for IDing on our website that was done by Yuqin Liu, who's a graduate student, and this is our website. This is a spectrum of 90 BW at late time, so back then in the 60s we could have predicted where the next skyscraper is, which is right here. And we also release our code. So not only do we release our spectra, which is good but also hard because you have to make sure that all your spectra are in the same homogeneous way, but you're also publishing our code because usually that's the most important part between your spectra and your result. So in terms of implication of IDing, as I mentioned, a lot of the 1Cs turned out to be 1Bs. And that has actually a number of implications. One of them is for rates. So as you may know, in 2011, the LOS Supernova team, which has a beautiful volume-limited survey, mentioned that the rate between 1Cs, which are the most stripped, or supernova from the most stripped stars, and 1Bs is around 2.6, which is a very large value. How do you make stars that are such highly stripped, almost twice or 3 times more common than less stripped ones? So that was actually a big puzzle that led to a number of people saying, well, perhaps you have hidden helium in 1Cs. Luc Dessart and others mentioned that. But when I presented this work in 2014, talking with Isaac Shivers, who is a graduate student at UC Berkeley, who's also here in the audience and has a poster, we discussed re-IDing the Berkeley supernova, or the supernova that went into the LOS volume-limited survey. And he just has a paper out, the poster out, the paper will be submitted soon, and he finds that actually 1Bs are more common. They seem to be 2 times more common than normal 1Cs, while though the total fraction of stripped envelope supernova is still 30% of all core collapse supernovae. So this new updated rate is really important for constraining progenitor models for these kinds of stripped envelope supernovae. Or Grauel will have a paper out soon about the LOS supernova rates revisited as a function of galaxy property and what that might tell us about the supernova progenitors. So in terms of the progenitors, as Adam mentioned before, these are still one of the main outstanding questions. And for the stripped envelope supernova, the question is, how were the envelopes stripped? Was it in a single star system, a single massive Wolf-Rayet star that has metallist-dependent winds? Or was it in a binary where the Roche lobe overflow or some other kind of interaction with the companion removed the outer layers? And of course, this is an important question that affects a lot of fields, including also fields at high redshifts, given the connection between broadline type 1Cs and GRBs. Now, it's tricky because the direct way of getting progenitors has not been successful, except perhaps recently. There were 2 papers on IPDF13 BVN last week for most of the nearby 1Bs, 1Cs, and broadline type 1Cs. And of course, this cannot be done for GRBs, since they are large distances, nor for superluminous supernovae. So we need other ways and statistical studies to understand what the progenitors are to do stellar forensics. So you can look at supernova and GRB properties. I'll discuss those venues today. Or you can also look at host galaxy environments and supernova rates, and also flash spectroscopy that we will hear about later, but I will not discuss this in detail. Okay, so how do we get progenitor masses or ejecta masses from supernova properties? So for non-1As, the light curve is set in terms of the total luminosity by the amount of Nichols 56, and the width is set by a combination of ejecta mass and kinetic energy. But the point is that the width is set by both, by 2 parameters, and so you need 2 observables to break the degeneracy between ejecta mass and kinetic energy. So you need both light curves and spectra to do so. So this has been attempted by a number of different groups over the last many years. Drought, who's here, Kano, Lyman, and Tadia, using various combinations, mostly light curves, and then assuming certain velocities. But here with this data set, the CFA data set, we have both light curves and spectra. So we can determine, and that's what's been doing by Federica Bianco in PrEP, that's going to be out soon, where we find, along with other groups, that the ejecta masses for most stripped envelope supernovae are on the low side. They're usually between 2 to 4 solar masses, much lower than you would expect from a single massive Wolf-Rayet star. However, there's a number of caveats to keep in mind that Fed goes into. One is that the absolute values in these ejecta masses are uncertain by a factor of up to 4. Depending on what kind of opacities you assume and how you parameterize the light curve width. So that's really important to keep in mind. And what we should be doing is actually comparing in terms of relative amounts the ejecta masses between different subtypes of supernovae. And the second aspect that was raised by Wheeler recently is that we might be just sensitive to the ionized ejecta. And so that's why it's much smaller than the total ejecta that you would expect it. So now we also, and looking at just spectra, we can now quantify the diversity of 1Cs, and or in general, various kinds of subtypes. So we just did that, a paper that was posted 2015 and got accepted recently. So this is, these are the mean spectra of 1Cs as various phases. And what we could ask was, is 94I, which was the most nearby 1C that everybody loves, and always claims as the prototypical object, including shown on Jochen Greiner's plot comparing superluminous supernova that they saw with other 1Cs, is it a typical 1C? And so the answer is no. It's not a typical 1C. As you can see here, the spectra are more than 1 standard deviation, as well as reaching most of the time maximum deviation in the spectra. So 1C, the 94I is not a spectroscopic 1C, nor is it photometrically, as other people have shown. Now, what about 90BW? It was the closest supernova GRB, and it turns out this one is a typical broadline type 1C, at least spectroscopically. So a lot of people use 98BW as a template to do K corrections for supernova GRBs at high redshifts, and the good news is it's warranted, so you can continue doing that. But now it tells us that we also now have a different way to compare supernova to each other. Before, and many conferences before, you would go and people would say, well, this new object looks like O2AP at maximum, but at later times it looks like this other supernova that only few people had heard about. So now it was really back then comparing to supernova as saying, well, it has the nose of the father and the ears of the mother. But these days we can do better work. We can use standard deviation and maximum deviation and mean spectra to statistically compare supernovae. And that's been done by Triadol in a recent supernova GRB paper. So the other thing we did was we separated broadline type 1Cs with and without spectra. So we had also similar mean spectra with broadline types without spectra, without GRBs, and broadline type 1Cs with GRBs. Because the big question that we have is, what is the difference between supernova that are able to produce a relativistic outflow and others that don't? So when we do that, we find that those without GRBs seem to have, or the other way around, broadline type 1Cs with GRBs seem to have broader spectral lines than broadline type 1Cs without observed GRBs. And you saw that earlier by Jens, but the plot was really not easy to read. So here's a cumulative distribution plot that shows you the width. This was called the convolution width velocity for both broadline type 1Cs with GRBs, so in red, and broadline type 1Cs without GRBs. And broadline type 1Cs with GRBs have higher widths. They not only have higher widths, but also higher absorption velocities as measured by the absorption trough. So here, the broadline type 1Cs with GRBs in red, they have the highest velocities. These are the rolling weighted means. Then broadline type 1Cs without GRBs have lower values, but still high compared to normal 1Cs. So what we did was we used a novel method to measure the widths. Nobody before had really tried to do a very kind of systematic attempt, but we use a template fitting method where we use the 1C mean spectrum and convolve it with a Gaussian to mimic the smearing and broadening that we see in broadline type 1Cs. Okay. So it's clear that broadline type 1Cs without observed GRBs have lower velocities by around 6,000 kilometers per second than broadline types with GRBs. So what could be the reason? Could it be perhaps, and that's one explanation that we favor, could it be that these broadline type 1Cs without GRBs have even more choked lower energy jets compared to supernova GRBs, in particular compared to the low luminosity GRBs that a number of people that we heard earlier suggest that these are from objects that had shock breakout due to the relativistic jet, but we don't see the relativistic jet. So to answer this fully, we really need more modeling about the jet supernova eject interaction. So Andrew is interested in how the jet is able to get out of the star. Thanks. But the next point is there any way that the jet has an impact on the structure of the stellar envelope that then will become the supernova ejecta? So as we saw earlier, we don't see any relationship or any correlation between the GRB property, including luminosity and energy, and also collimated corrected energy, between the supernova, so between the GRB luminosity and the GRB energy and the supernova absorption velocity. So it seems like even though the supernova knows whether there is a GRB pointing towards us, it does not care about the strength of that jet. So now the question about hidden helium. So one worry was that, well, perhaps you don't see the helium because it's smeared out by the high velocities. So to check that suggestion, we took a normal 1C and smeared it out and saw, could you just get rid of the helium lines that way? And the main point is that we cannot. So if you have you take a 1B, you make a broadline 1B by smearing it out fully, you still would be able to see in red the helium lines. They have been broadened, but they haven't been smeared out fully. So they're still present, but we don't see those in the spectra of broadline type 1Cs. So they're truly broadline type 1Cs. So it really means that the progenitors of supernova GRBs are truly helium-free, and it's really hard to make a truly helium-free progenitor at such low metallicities as those supernova GRBs are observed. So that points towards binaries, something that Salma will discuss later. So what about normal 1Cs? Could normal 1Cs have hidden helium? So Luc Dessart suggested this in a 2012 paper, and what he also did, which I think is great, is he made predictions of how the velocities would behave of objects, of progenitors, where you hide the helium envelope. And so he predicts that the velocities of 1Bs that are fully mixed should be higher than the velocities of 1Cs that are not well mixed. And so we tested this with the large data set of 21 1Bs and 17 1Cs, and we find, especially when we look at the roll-out weighted mean, that actually the data show you a trend that's opposite to the predictions. So the 1Bs have lower velocities than the 1Cs. So again, it looks like there's no hidden helium even in 1Cs, normal 1Cs, and that's in agreement with Tadi et al. 2015 that have early time light curves of Sloan supernova, and Haring et al. Who computed that you could hide only less than 0.1 solar masses of helium. Okay. So now the question that also people ask is to be or not to be. What does it take to be a type 2 supernova? As I mentioned, type 2Bs are characterized by a little bit less hydrogen in strength, but also helium. So they sound very similar to 1Bs. And it turns out 1Bs also have some hydrogen left. So what we did was we did a careful analysis of all the hydrogen strengths. And so here you see as a function of time the equivalent width of hydrogen that shows you the strength for a big, large data set. So on the one hand, there is a continuum of strengths of H alpha for 1Bs and 2Bs. So even 1Bs seem to have some hydrogen, but very weak. However, the lines never cross. So this idea that people worry that would be fully time dependent, so what if you don't have early time data and you see an object late times, you would perhaps misclassify, is not warranted. So that worry is not warranted. However, as I mentioned, there's a continuum of strength. So in terms of future reports, it would be great to not just put them in two big buckets of 1B or 2B, because there is a physical continuum which you would expect from progenitor models, that you have a range of hydrogen envelopes intact before explosion, but rather that we should perhaps report the strength of H alpha at some phase to be able to really put it in this plot that encompasses much more data than the two big rough bins that we usually have been using. Okay, last but not least, we talked about asphericity earlier. Adam showed us the nice data of Cassay. So the question that we can ask is, could asphericity be the reason for the diversity that we see in 2Bs? And Cassay is a beautiful object to test this, because we have light echoes. We have a number of light echoes such that we observed Cassay from multiple lines of sight. So this is a paper by Rest et al. That shows you the 3 viewing angles for Cassay. And what they did, which was hard and time-consuming, was they took spectra as a function of viewing angle, as if we could have flown there and put our telescopes from different viewing angles. And what he found was that these light echo spectra had different velocities depending on the viewing angle as compared to these two supernovae. And you always have to do this comparison to have a supernova, convolving them through the light echo, because the light echo itself is actually what it does, it takes the input spectra and convolves it with a certain kernel, and that's what you see, light-weighted average spectrum, basically. So you have to always compare it to various supernovae that you propagate through the light echoes. So what we set out, and that's what Kiran Finn did in the paper that we submitted recently, is we asked the question, could the asphericity as seen in Cassay explain the diversity we see in terms of the spectral velocities for a large data set of 2Bs. So this is a busy plot, but the main point, since I'm running out of time, is that the range in velocity due to asymmetry is completely consistent with the velocity diversity that we see in type 2B supernovae. And we had to do this careful analysis where we had to take the various supernovae in our sample and propagate them all through the light echoes. So it's very completely consistent with the hypothesis that the velocity diversity of 2Bs is set by asphericity alone. Okay. So now I'm coming to my conclusion. So we have started a really exciting era of statistical analysis of both normal and exotic core collapse supernova that we'll hear about. So it's really beautiful treasure trove to look at old questions in new ways with large data sets. So let's get our supernova IDs right. So it's a very important first step. It might sound perhaps trivial to some of you, but it's a very important aspect. And now with a larger spectral library and with correct IDs, we can do this in a more thorough fashion now. In terms of the statistical analysis, just want to highlight a few things. One is there seem to be no hidden helium in 1Cs and broadline type 1Cs. So these kinds of progenitors are hard to produce, especially at low metallicity for supernova GRB. So I'm looking forward to the efforts of our modeler friends. And it seems like broadline type 1Cs seem to know about the GRB pointing towards Earth, but they do not care about how strong that jet was. In terms of next steps, I think the next steps that are very exciting and have been already done for a few objects is to go either very early or very late. So early time, very kind of hours after the explosion, getting data, both spectroscopy and photometry, that tell you about the cooling envelope emission that could constrain the radius of the star, or flash spectroscopy that can give you a spectrum of the star before it exploded. And also very late, as shown by 14C, that Rafael Amurgudi and others have been working on, where they saw actually late time transitioning of a 1B, this 14C. And of course, the next step is also to do panchromatic observations using radio and X-ray observations. The other thing is also, now that we have large data sets where we find statistical trends, this is a real challenge for our friends in the supernova and massive stellar modeling game, because it's no longer enough to look at one spectrum and one object and carefully craft a model that explains the observables. Now we actually have to explain the statistical trends that we see based on large data sets. Thank you.
So, Maryam, do you see in your data any evidence for 1B broadlined events? And if not, do you have an idea why? I mean, is it a progenitor structure different enough that this whole picture of a jet choking inside the star and giving you broadlines in a 1Cs just doesn't work for the 1Bs?
So in terms of your first question, so I know that there have been claims by others saying that there are helium lines in some supernova GRBs, or broadline type 1Cs. It's really tricky, and we can talk offline. I would say there's no strong evidence for helium in any of the supernova GRBs, nor in broadline type 1Cs. So,
but I mean 1Bs that are broadline.
So no, we see no evidence for that. As I mentioned, both statistically and also one by one, there are no broad helium lines that we see. In the optical, in the near-infrared, people worry or have been claiming that there's this 1 micron helium line, but that could be due to many other elements. You really need a 2 micron, and that I don't think has been seen. In terms of what it takes, well, it must be really highly stripped somehow. So that's a big question. The environments are different for broadline type 1Cs compared to 1Cs even, so they might have even more extreme progenitors and some other mechanism to strip them fully down.
If we had atomic or something similar, and I know this is not something I should be mentioning in Cambridge, you'd be able to break some of this degeneracy because you got independent information about the masses, the velocities, and the energies of the explosion. So you have complementary information that help you break this.
So remind me again, and others, what is Hitomi again?
It isn't.
Okay. Oh, that's the
Gamma ray hard X-ray data
exactly,
will give you an independent look at exactly some of many of these questions.
Yes.
And
yes,
so
it would be great.
sometime in the future would be great for
Yes.
nearby. I just thought I'd mention it for those who care.